All right, it's Tuesday here, and we're going to be starting our final chapter of the first unit of Physics 1151, Chapter 21, which deals with the second law of thermodynamics, heat engines, and refrigerators. And so this picture here is a picture of a coal-burning power plant. Um, and there's a pretty good bet that this one of these is likely producing the energy that's used to power our computers, our laptops, our lamps, and pretty much everything else in our home. Hopefully we're weaning away from this, but as of today, it's still being used to power quite a bit of our energy, supply quite a bit of our energy. And this is an example of a whole class of thermodynamic systems called heat engines that we're going to be studying today. And the heat engines behave, they have differences in how they work, but they all have some of the same general features. So with this power plant here, what happens is they all have a source of energy, and more usually what it involves is the burning of a fuel. Okay, and in this case, it's the burning of coal in a furnace. Okay, and that produces a large amount of heat. In an analog is with a four-stroke engine, you have the burning of an air-gas mixture by the ignition of a spark plug. So you have a large amount of heat being generated by the burning of a fuel. And that heat is used to do mechanical work, which is used in this case to generate electrical energy, which is supplied to the power companies, which is supplied to you and I. And in this case, that burning of coal and that generating the large generation of heat in the furnace is used to boil water, and that latent heat from the boiling creates a high pressure steam. And that steam is used to rotate a turbine, which is connected to a generator. And so some of this heat is used to do mechanical work. It's used to rotate the turbine. Just as in an automobile engine, the heat generated is used to turn a crankshaft. Okay? Now the rotational kinetic energy of the turbine gets converted to electrical energy through Faraday's law. We'll deal with that later in the course. And that electrical energy is the useful energy that is generated by the power plant. Now, not all of this heat is used to do work. As you see here, some of this steam is exhausted as waste heat, and that energy is lost by the system, okay? Just like some of the heat is exhausted in an exhaust manifold of a car engine. So there's certain features that are common to all of these types of what we call heat engines. They all have a fuel, and the burning of the fuel generates a large amount of heat, and some of that heat is used to do mechanical work. And in this case, with a coal-fired power plant, that mechanical work generates electricity. And then whatever heat is not used to do work is exhausted as waste heat. And this is an example of a heat engine. So we're going to cover that today. And then we're going to cover the reverse of a heat engine, which is a refrigerator. And that's used to pump heat out of a cold room or a cold up body and discard it into a warmer environment. So we're going to cover both of these. We're going to start off before that with a quick review of the first law of thermodynamics. Then we have to do a little bit of nomenclature here. We're going to define the work done by a system, as we've been discussing work done on the system. Then we need to briefly talk about cyclic processes and the second law of thermodynamics. And then finally we will get into heat engines and refrigerators, air conditioners, and heat pumps. Assignment 4 will be due next Thursday night. And Unit 1 exam, as we've said many times, will be held on Monday the 22nd of this February. Here's the learning objectives. This is what you should be able to know after you read the book and after you've done your homework problems and we've covered these notes. So this, for an exam, are the types of things that you need to know. So just a quick review here. We're discussing in this unit thermodynamics, and it's just a big word, meaning it's the study of processes in which energy gets transferred as heat and work. And remember that heat is the transfer of energy from one object to another due to a temperature difference between the two, right? Heat is transferred from a warmer body to a colder body. Okay? And work is the transfer of energy to and from a system due to some mechanical work that's being done on the system. For example, expansion and compression of a gas. And both heat and work can have the effect of changing the microscopic energy of the system. In other words, it changes the system's thermal energy, its temperature. So we've already covered thermodynamics, which is just energy conservation to include heat and thermodynamic processes, and we'll review that real quickly again in a minute. That's the first law of thermodynamics. Then we're going to cover the second law of thermodynamics, which explains why processes in nature tend to go in one direction but not the reverse direction. So we'll cover that in a little bit. So quick review, first law of thermodynamics. Recall that the first law of thermodynamics stated that the external work that was done by the environment on some system, maybe an enclosed gas, plus the heat added to the system is equal to the change in the thermal energy of the system. And then we always have to be careful of the sign conventions, right? Where positive values of Q imply heat added to the system from the surroundings. Negative values of Q refer to heat removed from the system or transferred to its surroundings from the system. And then work, remember external work, to calculate the work done on the system. We can take the area under the PV curve going from the initial state to the final state, and that's W external. And external work is greater than 0, positive value, if work is done by the surroundings on the system. For example, the gas is compressed, that's positive external work. And work done on the system, the external work, is negative if the work is done by the system on its surroundings. For example, when a gas expands, the external work is negative. And recall that the thermal energy depends only on the initial and the final states of the system. And for a gas, that only depends on, ideal gas, that only depends on the temperature. So that's the first law of thermodynamics. Recall that changes in the state of the gas system we would represent on a pressure volume diagram or a PV diagram. And we use these diagrams to calculate things like work. By the area under the curve, we can get work. And then work along with the first law of thermodynamics. If we know work and we know heat, we can relate that to the change in the thermal energy. And so for an ideal gas, we would use this first law of thermodynamics along with calculation of work. And for an ideal gas, the ideal gas law, and we would relate the changes in the heat and the work to the changes in the state of the system, its temperature, pressure, and volume. And so these three equations, these are important. You should be able to calculate work from a pressure-volume diagram for the various processes. You should be able to use that work along with to relate heat, work, and the change in the thermal energy of the system. And so for that, you need the first law of thermodynamics. You need to be able to calculate work. And for ideal gases, we will also need the ideal gas law to relate pressure and volume to temperature and hence thermal energy. And so these three equations are very important in our study, and I encourage you to put them on your cheat sheet. Now, the sign convention of work is often confusing. So one way that I remember it is I look to see if the gas is expanding or it's being compressed. And in this case, for example, final volume is greater than initial volume, and so the gas is expanding. And remember, if it's expanding, the external force and the displacement are in opposite directions, and so the external work will always have a negative sign. And so I know for an expanding gas that W external should be a negative number. Okay. Once I know that, I can just worry about calculating the area under the curve, which is just the integral. We count squares here. And I can take that absolute value of the area under the curve and I can tack on a negative at the end because I know it's an expansion. And so if you tend to get overwhelmed with these sign conventions, I find it easiest as just a consistency check or as a starting point to determine whether it's an expansion or a compression, and that will give me the right sign there, and then I can just worry about calculating the area under the curve. So that's calculating work. We discussed the types of processes that we discussed so far. Was first a process at constant volume, and that was called an isochoric process, and that's delta V equals 0, then meaning the volume doesn't change. Remember, that's a rigid container, maybe for gasoline. Then we discussed an isobaric process in which the pressure doesn't change. And then an isothermal process, which is constant temperature, and then an adiabatic process in which it's either well insulated so that no heat enters or removed, or it's that the process of expansion or compression happens so fast that no heat can enter or leave the system. And then for each of these processes, you should know what's constant. And then in the ideal gas law, we use the values of whatever is constant. For example, a constant volume and a constant number of moles means the ratio of P over T is constant. So you should be able to use that to relate pressure and temperature in an initial and final state, and so on for what's constant from the ideal gas law in the other processes. You should be able to, given this definition of the process, you should be able to calculate work and calculate the heat added to or removed from the system. So this table is very important, and I encourage you to use this in your exam preparation. So you need to understand these four processes very well and how to relate heat, work, and the state variables of the system. So that's our review up to this point of the first law of thermodynamics. Now, when we start talking about engines and refrigerators, it's often more convenient to discuss the work, to express the first law of thermodynamics in terms of the work done by the system, for example, by the gas, rather than the external work done on the system, which is the work done on the gas. And it turns out that they're just the opposite sign, but the same magnitude. And to see that, here's our little piston here. So suppose that the gas is expanding here. And so there's two competing forces, right? The pressure of the gas pushing on the piston outward, and that's in the same direction as the displacement. So this would be positive work done by the gas. Now, there's an equal and opposite force, the external force acting on the piston, which is pushing back on the piston in the other direction. And for an expanding gas, the external force is in the opposite direction as the displacement, and this means that the external work is negative for an expanding gas, and the work done by the system, by the gas on its surroundings, is a positive number. And they're the same force magnitude, and it's the same displacement, and so the work is the same magnitude, but they're opposite in sign. And so the work done by the system, which the author calls WS, is the negative of the work done externally by the surroundings on the system. And for a compression, it's just the opposite. The external work is positive, and the work done by the system on the surroundings is negative. So that's often the easiest, is just to remember whether it's a compression or an expansion, tack on the appropriate sign, and then calculate the area under the PV curve to get the magnitude. So if we write the first law of thermodynamics, which is right here, first law says that W external plus Q is the change in the thermal energy. And for W external, we put in negative work done by the system. The first law of thermodynamics can be written as this. And we often isolate Q on the left-hand side when we're dealing with heat engines and refrigerators. And so let's write the first law like that. So what the first law says is that the heat added to a system is equal to the work done by the system on its surroundings plus the change in the thermal energy of the system. And for an engine, what this means is that the heat added, some of the heat added Q goes into work done by the system, and the rest goes into changing the thermal energy of the system. Not strictly true, because an engine's a cyclic process, which we'll deal in a minute, but this is the first law of thermodynamics in another form in terms of the work done by the system. So when we start covering engines and refrigerators, these thermodynamic processes are what are called cyclic. And what that means basically is that these temperature and pressure and the volume, these state variables, change over one cycle, and then they return to their same values after the cycle, and then the process repeats. So for example, a 4-stroke engine, there's 4 thermodynamic processes, and then it repeats itself on the temperature, pressure, and volume all return to their same values after every cycle. And in terms of the PV diagram, if pressure and volume return to their original values after one cycle, then this PV curve is a closed loop. Okay, for example, suppose the process starts right here at Vmax, and you get a compression to a smaller volume, and then an expansion, and the volume and the pressure return back to the same values after one cycle. And so for a cyclic process like a heat engine, the PV diagram is a closed loop. And if it's a closed loop, it turns out that the work done by the system or on the system over one complete cycle is just the area enclosed by the loop. And this is very important. We're going to use this for calculations. And we can see it right here in this picture. So if we take this closed loop here, and we take the top part of this curve, this is the expansion going from smaller volume to larger, and we calculate the area under the curve. This is an expansion, right? And so the work done by the system is the positive value. The area under the curve is positive. Now if we look at the second half of the cycle, now we're going through a compression, which means larger volume to a smaller volume, and that means the work done by the gas is negative, and so this area under the curve during the compression is negative. And when we add the positive work to the negative work to get the total work done in the cycle, it's just the area enclosed by the loop. And so we have the general result that we're going to use in this section quite a bit, that the work done in a closed cycle by the gas, by the system, is just the area enclosed within the loop. So let's start by an example. With an example here. So we have 4 thermodynamic processes, and each one is a cycle. It's a closed loop. And so the question is, rank from largest to smallest the amount of work done by the system in each of these processes. And so what that involves is calculating the area enclosed by each loop and determining which one is the largest. Okay, so let's go through the solution here. If we assume that the pressure is in pascals and the volume is in meters cubed, so that the area, which is length times width, is joules, then each of these squares would correspond to 1 joule. So let's look at the area for each process. Okay, so first process here, which we'll call process 1, the height of this rectangle is 1 square, 2 squares, 3 squares. Typo. The width is 1 square, 1 meter cubed. The height is 3 pascals. And so the area, the work, should be 3, typo, pascals times 1 meter cubed is 3 joules. 3 newtons times meters, which is 3 joules. And so that's a typo. That should be 3. So WS1 should be 3. Okay. Let's go over to the second process. Okay. Here the height of the rectangle is 1 pascal, and the base is equal to 1, 2, 3 meters cubed. And so the area is 3 squares, or 3 newtons times meters, which is 3 joules. And so the work done in process 2 is the same as the work done in process 1, 3 joules. Now we go to process 3, and this is a triangle, right? And so to calculate the area enclosed, it's 1/2 of the base times the height. And the base is 3 meters cubed, and the height is 3 pascals, and so the area is 4.5 joules. And you can do the same for process 4, and we get 1.5 joules. And so the work done by the system in process 3 is the largest. It's 4.5 joules. 1 and 2 are tied. Again, remember the typo. 1 should be 3 joules, 2 should be 3 joules. And so these two should be tied. WS1 and WS2 are 3 joules. And then the work done in process 4 by the system is the smallest. It's 1.5 joules. And so you should be able to, for any cyclic process with simple geometry, you should be able to calculate the area enclosed and use that to compare work. So how does the first law of thermodynamics, what does that say for a cyclic process? Okay, so we go back to the first law here, and we can write it as, remember, Q is Ws plus delta E thermal. Okay. If the process is cyclical, that means the temperature and the pressure and the volume return to their original values after one full cycle. So if the temperature doesn't change, delta E thermal is always 0 for a cyclic process. And so we can write that as equal to 0. And what that says is that Q is equal to Ws. Now we need to define with engines what Q means. So in this case, for an engine, Q is the net heat flow into the system, which would be the positive heat flow from the warm reservoir into the system, Q hot, and the flow out of the system, Q cold. And so Q in this system here is the net heat flow, right? And it's positive coming in, negative coming out. So we can write Q as the difference in the absolute values of Q hot minus Q cold, where Q hot is the heat entering the system from the warmer body, and heat leaving the system, Q cold, is to the cold, leaving from the colder, heat leaving the system to the colder body, exhausted. And so we can write this first law of thermodynamics, which is a useful form for engines and refrigerators, as the heat added goes into doing work, and the rest is exhausted into the cold reservoir. And this is displayed using this energy transfer diagrams, which we're going to discuss a little more here, where you have heat entering, positive QH, some of it is going into doing work, and some of it is going into doing it being exhausted into the cold reservoir. And we can get rid of these absolute signs if we remember that all of these are positive quantities. So now that we've discussed the first law of thermodynamics, there's another law of thermodynamics which is very important, and it governs why processes only go in one direction. So we all know from experience that heat flows from a hot body to a warm body, right? Heat energy goes from hotter to colder. You never see energy or spontaneously going from a colder body to a hotter body, right? It just doesn't happen in nature. Now it wouldn't violate the first law of thermodynamics, but it just doesn't happen. And another example is a ball just doesn't absorb thermal energy and fly up into the air, right? Processes only go in one direction, right? For example, you drop a ball, it hits the ground, and that potential energy that we use to raise the ball goes into kinetic, and finally it goes into heat, thermal energy. But it doesn't go the opposite way. So the second law of thermodynamics is used to explain why processes in nature only go in one direction. And this has a lot of examples: heat engines, refrigerators, chemical reactions, and biological processes. So we're going to explore this second law of thermodynamics in terms of heat engines and refrigerators. So there's several different ways that you can write the second law of thermodynamics. They're all equivalent, it's just different ways of writing it. And basically, they all just state why processes only go in one direction. And so one way of writing it is in terms of heat flow. In other words, if you have an object at a higher temperature, one body at a lower temperature, and you put them in thermal contact, heat will always flow from the hot body to the cold body spontaneously, but it won't spontaneously flow from the colder body to the hotter body. So that's one way of expressing it. Heat goes in one direction. The second way we'll see is in terms of heat engines, and it says that it is impossible for any engine to completely convert heat into mechanical work. Some of the heat always goes into waste heat, which is exhausted. We can never completely harness all of that heat into useful work. Yet another way of writing this or expressing the second law of thermodynamics is that if there's no spontaneous transfer of heat from cold to hot, and so if we want to remove heat from a colder body, like a refrigerator, and kick it out into a warmer body, the room, it doesn't happen spontaneously. We need to apply work in order to move heat against the temperature gradient, right? In order to force it to go from cold to hot. And then the process that, the description that encompasses all of these, we're not going to cover this today, entropy, but we're going to get to it eventually. And what this means is that in any process in nature, the amount of available energy to do work decreases. In other words, the disordered energy in the system, the energy that's unavailable to do work, always increases in any process. We never go from more ordered or less ordered to more ordered. And so one way of doing this is you can take some black jelly beans and some white jelly beans, and you can dump them into a container. And you can dump all the white ones in first, and you can dump all the black ones in second. And you'll have this stratified mixture where all the white ones are on the bottom and the black ones are on the top. And the jelly beans are ordered, right? They're stratified. Now, if you shake the jar up, the order will always decrease, right? They'll become random. And so the black and the white get mixed up. So now you have more disorder in the system. And you can shake this thing up 1,000,000 times, and it will never go back to the same ordered, stratified distribution of jelly beans that you started with. So in other words, processes in nature will always go from more ordered to less ordered. And this generalization basically says that the entropy always increases. So we'll cover that later. We're going to focus primarily on heat engines and heat flow and refrigerators. So let's start with a heat engine here, and we're going to draw this process using what's called a heat energy diagram. So a heat engine, whether it be a coal-burning power plant or whether it be a four-stroke automobile engine, always has a hot reservoir, and in this case that would just be the furnace in the case, the hot furnace in the case of the coal-burning power plant, which is a source of heat. It's at a high temperature. Some of the heat will flow into the system and will be extracted as work. It'll be used to rotate the turbine. The rest of the heat will be exhausted into this cold reservoir, which is just the atmosphere. And so we have a hot reservoir, which is the source of heat. That's some of the heat is being used to do work, and the rest is exhausted from the system into the cold reservoir. And so we draw our arrows as shown. Heat enters the system at a higher temperature. Some of it does work. We call that W out, and the rest of it goes into exhaust. And this process repeats itself over and over and over, and it's a cyclic process. So the heat energy is typically from a burning fuel. Some of it's used to do work, and the rest of it is waste heat. And so that's the general process of a heat engine. We use heat, and we convert some of it into work. And that work can be used to generate electricity, or it can be used to turn the wheels of a car and move the car. Okay, so it goes into work. So let's look at the video here.
A basic lesson in the fundamentals of a four-stroke EFI gas engine may be helpful to your understanding of Mercury products. Here are the basic components of every four-stroke gas engine: a piston, a connecting rod, a crankshaft. As the piston travels up and down in the cylinder, this lateral motion is turned into a rotating motion at the crankshaft. The longer the stroke of the piston, the larger the displacement of gas and air occurs in the cylinder. To propel that piston, we need to ignite a tiny bit of gas and a whole lot of air. This creates expansion inside the cylinder. The fuel delivery system consists of an air intake manifold, valves, intake and exhaust, a fuel injector, and a spark plug. A four-stroke engine is called a four-stroke because 4 up and down motions are needed to complete the cycle. In the first stroke, the piston travels downward as the intake valve opens and a mixture of air from the atmosphere and a metered amount of gas from the electronic fuel injector enter the cylinder. This is called the intake stroke. On the second stroke, the piston travels upward, compressing the air and fuel to make a highly combustible mixture. This is called the compression stroke. At this point, the spark plug fires, sending the piston downward from the expansion of the air and gas mixture. This is the combustion stroke. Opens to release the burned air-fuel mixture. When the piston reaches the top of this stroke, the intake valve opens and the cycle begins all over again. It takes 1 up and down motion, or 2 strokes of the piston, to create 1 revolution of the crankshaft. RPMs, or revolutions per minute, is how many times the crankshaft rotates within that minute. At wide open throttle, the crankshaft may turn at 5,000 RPMs, or a dizzyingly 83 times per second. Meanwhile, the piston traveled up and down 166 times in that same second. Want to see how fast that is? Now, that's fast. Let's see it again. Amazingly, the four-stroke EFI engine does this smoothly, quietly, and reliably for years and years of operation.
So the four-stroke engine, the internal combustion engine, involves 4 steps, and we're going to go over these a little more later. And each of these can be modeled as one of the types of thermodynamic processes that we covered before. And so the intake stroke, where the air comes in and expands and the gasoline mixes with the air, that can be approximated as an isothermal expansion of air. Then the second stroke, the compression stroke, where the intake and the exhaust valves close and the compression happens so rapidly that heat cannot be added or removed. We can model that stroke as an adiabatic compression. Then when the spark plug ignites and it generates a huge amount of heat, which expands the piston. Again, this happens so rapidly that we can assume that negligible heat enters or leaves, and so we can approximate that combustion stroke as adiabatic. And then finally, the exhaust stroke is when the valve opens to discard the heat and the volume goes back to its original value. That approximation is approximately isothermal. So these 4 processes, when you add them all up, give a complete cycle, and that's why it's important to understand each of the processes individually. So it turns out that for any engine, we can define the engine efficiency with this Greek N-looking, eta is looks like an N. as the work output of the system, in other words, what we get out of this system divided by the heat input to the system. So it's what comes out divided by energy out over energy in. And so the efficiency of a heat engine is just the work done by the system divided by the heat entering the system from the high temperature reservoir. And the second law of thermodynamics states that it's impossible for all of the heat to be converted into work. If it did, there would be no heat exhausted into the cold reservoir, and we know that that is always the case. So, in other words, there is no such thing as a perfect heat engine. Some of the heat always is discarded as waste heat, and we can never get out as much work as the heat that we put in. Here is the heat energy diagram for a heat engine. So we have, well, actually, I'm sorry. This is an example of a heat energy diagram just for a copper bar, which is in contact with a hotter body, maybe a stove, and a colder reservoir, maybe your hand. Hopefully you wouldn't do this, but suppose you did. And so we know that heat spontaneously flows from the hot reservoir to the cold reservoir. And so this energy transfer diagram, we draw an arrow pointing from hot to cold, and that's the heat entering the system, the copper bar from the hot reservoir. And we draw the arrow going toward the cold reservoir, your hand, in this direction. And so these energy transfer diagrams are basically just diagrams which show the first law of thermodynamics as far as magnitudes, and the arrows show the directions. So here's an example of a spontaneous flow from a cold reservoir to a hot reservoir. So here's your hand, here's the warm stove, here's the copper bar. We know that energy does not flow from the cold body to the hot body. And so this description here doesn't violate the first law of thermodynamics. It just says the energy transferred here exits the system, but it violates the second law because we know that heat does not spontaneously go from cold to hot. And so these energy transfer diagrams just relate the two heat flows, and then if we add work to the process, like with an engine, you would draw the energy level diagram as a hot reservoir, a cold reservoir, and then the output work. And Q hot is equal to the work plus Q cold. And so your arrows show the directions, and the magnitude of the arrow, Q hot, is equal to the sum of the work plus the exhaust heat that's discarded. And so you should be able to draw these diagrams for different thermodynamic processes. Let's do an example here. So we're going to rank from largest to smallest the work output performed by the heat engines, and then the efficiency, which is the output work over the heat in. And so each of these four engines, the Q hot, Q cold, and the work are drawn on this energy level, or this heat transfer diagram. So in this first diagram, Q hot is 100 joules of heat enter the system from the hotter reservoir. 60 of it is exhausted, and this means that the work output must be 40 joules. So of the 100 joules of heat, 40 of it is used to do work, and 60 of it is exhausted. Okay, so W out is 40. For the second process here, 200 joules of heat enter the system. 160 joules are exhausted as waste heat. that means that the work output must be 40 for this one as well. And so the work done by the engine A is the same as B, 40 joules. We look at C, 60 joules come into the system from the hot reservoir. 90 joules come in. 60 are extracted as exhausted as waste heat. That means the work done is 30. And so WC must be less than A and B. Let's look at the last one. 90 joules of heat enter the system. Only 40 are exhausted as waste heat, and so 50 must be used to do work. And so that this system here does 50 joules of work, and so the work done by D is the highest, 50 joules, followed by A, which is 40 joules. B also has 40 joules, so A equals B, and engine C does the least work, which is 30 joules. Okay. Now, in terms of efficiency, when you divide the work by the input heat, for engine A, 40 out divided by 100 in gives 40% efficiency of this engine. Engine B does the same amount of work, 40 joules, but it has 200 joules of heat coming in, and so that efficiency is only 20%, right? 40 out of 200, whereas engine A is 40%, 40 out of 100. So B is less efficient than A. Engine C, you have 30 joules of work and you have 90 joules of input heat, so the efficiency is 33%. Okay? And engine D is the most efficient. You have 50 joules of work out of 90 joules of heat. So D is the most efficient. A is the second most. It's 40% efficient. Another typo here. C is the third most efficient because it's 33%. And D is the fourth most, or B is the least efficient, which is 40. So you should be able to use these heat transfer diagrams to relate heat, work, and efficiency. Here's another example, example 2. I will leave that to you to work out on your own. And then we can cover that in our synchronous lecture on Monday if you still have questions. So in this case, we know the total energy, the rate at which energy work is being done, which we can use to calculate the work per cycle. We don't know the heat QH per se, but we know the engine is 20% efficient. So if we know the amount of work, we can calculate Q, the input heat. And if we know the input heat and the work out, the difference is given off as exhaust heat. So you should work this problem out on your own. Solution is given here, and we can cover this on Monday if you have any questions. So I think this is a good place to stop, and then we will cover refrigerators, air conditioners, and heat pumps tomorrow, and then we'll move into heat engines and refrigerators using ideal gases. So that ends it today. Have a good night.